Hi guys, so today's lecture is going to be on searching algorithms. In particular, we're going to be going over two different searching algorithms, linear search and binary search, as well as some interesting algorithm theory. So we'll go ahead and dive into the slides. So, and this is somewhat review for you because we talked about algorithms previously when talking about traversal through a linked list, if you recall. So an algorithm is a sequence of steps for accomplishing some sort of task. Searching, in particular search algorithms, the task is to find or search for some sort of element or key that you're looking for. And usually the sequence of steps involves something called comparisons, checking elements across the desired key or element to see if a particular list or data structure does indeed contain the element that you're looking for. So we're going to start with linear search. Linear search is a search algorithm that starts from the beginning of a list and checks each element until the search key or search element you're looking for is found, or the end of the list is reached. And so a common example of the linear search algorithm is searching through the elements in an array. So go ahead and look at an example of this. I'm going to go over to REPL.it, and you can see here I have my class main, and I have two methods. One is my main method, and the other is a method I've called linear search. The linear search method takes in two input arguments. One is of type int called element. In this case, element is the element that we're looking for, or the key that we're looking for. And the second input parameter is an array of integers, called simply array in this case. And this is what we'll be searching through for the desired element. And the return type of linear search in our case is Boolean here, representing true if the element indeed does exist within the array, or false if it does not. Other search algorithms oftentimes return the actual element if it's found, and null if it's not found. So yeah, in our main here you can see that we create an array of integers, and then we call this linear search algorithm searching for initially the value 6, and then after that searching for the value 7, and we're printing the results of that. Now we'll go ahead and dive into our linear search algorithm here. It's fairly simple, right? Here we have a for loop. This for loop I'm using the enhanced for loop syntax. If this part confuses you, then I suggest you go watch that particular lecture. And so we know that this is going to give us all of the elements within the array. And what we do is we check each item in the array and see if it's equal to the element that we're looking for. If it is indeed true, or if they are equal, then we know we have found the element or key that we're looking for. Therefore, return true. And if we go through this entire for loop without having found the element that we're looking for, then we know that the array does not contain the element or key that we're looking for. Therefore, return false. And it's as simple as that. Linear search is relatively simple. So we'll go ahead and run this. And so you can see here, it's printed searching for 6, false, which makes sense because the array does not contain the number 6. And then we have searching for 7, true, which again makes sense because we do indeed have the number 7. I'm sorry, searching for 7 and returns true because we do indeed have the number 7. So now conveniently here this enhanced for loop stops for us in case we do reach the end of the array. One of the convenient things of using the enhanced for loop syntax. But I could have also done the int I equals 0, I is less than array.length, I plus plus, and that would have been sufficient as well. So going back to the slides. So terminology here, an algorithm's runtime is the time the algorithm takes to execute. And not to be confused with terms like runtime, polymorphism. Those are two different uses of the same word runtime. In this case, in algorithms, runtime is talking about actual time, and namely how long it takes for an algorithm to run or execute. And so here's an example of algorithm runtime. If each comparison takes 1 microsecond, a linear search algorithm's runtime is 1 second to search a list with 1 million elements, and 10 seconds for 10 million elements, and so on, right? The example here is searching Amazon's online store, which has more than 200 million items, could require more than 3 minutes to search for the particular item you're looking for if you were using a linear search algorithm, which is a fairly long time. Imagine if you go into Amazon and you're looking for something and it takes 3 minutes per time that you search for it. I mean, in this day and age, that's incredibly slow. And so going back to this example here, a comparison, if we go back to our code here, a comparison is this right here. If the element is equal to the item, so the element we're looking for is equal to the current item in the array that we have, this right here is a comparison. And so what they're saying is that if each one of those in actual time takes 1 microsecond, and there's 1 million elements that you need to loop through, then the overall time it will take to find what you're looking for will be roughly 1 second. Okay, so we go back, let's continue presenting. So an algorithm typically uses a number of steps proportional to the size of the input. So for a list with 32 elements, linear search requires at most 32 comparisons. Now notice the at most part of that, right? Of course, that you might be able to find the element or key that you're looking for only within 1 or 2 comparisons. But it's what's at most that's really important. For example, 32 comparisons is not a big deal here, but imagine if we're talking about 200 million comparison elements. It's possible that that the list you're searching through doesn't contain the key you're looking for, and therefore you're going to end up making 200 million comparisons, which could take a very long time. So we tend to think of in terms of a worst case scenario. And so here we talk about 1 comparison is needed if the search key is found at index 0, 2 if the search key you're looking for is found at index 1, and so on up to 32 comparisons if the search key is not found. And so replacing the specific number 32 with a more generic number, in this case n, for a list with n elements, linear search thus requires at most n comparisons. The algorithm is said to require on the order of n comparisons. So where n is basically saying we don't know how large the list or data set that you're looking through is going to be. So we're going to think of things in terms of just this letter or this number n. And so linear search may require searching all list elements, which can lead to long run times if n is large enough. And that's what I was talking about before, right? Previously, 32 comparisons is not a big number, but if you talk about 200 million comparisons, or even larger, if we go back to the example, the Amazon example, let's say a billion items, that would require a very long time to find the item that you're looking for, which is not desirable. And so that's why different search algorithms exist. The next one we're going to talk about here is binary search, and it's faster than the linear search algorithm. But it does have a condition, though. So if the list of elements that you're looking at is sorted, there exists a search algorithm that is faster than the linear search algorithm, and this is binary search. So that is a requirement of the binary search algorithm, is that the list of elements be sorted. Sorted as in, if there are numbers, then sorted in ascending order might be 1, 2, 3, 4, 5, 6, 7, 8, etc. So binary search is an algorithm for searching a list if the list elements are sorted and directly accessible, such as in an array. So before we get into the steps here of the binary search, one of the trade-offs is, linear search, the code is very easy to implement. It's very easy for a human being to understand. Binary search, on the other hand, requires more overhead. And what I mean by that is it has more steps in it other than simply looping through each element in an array and comparing. So we'll go ahead and dive into the steps of the binary search. So binary search first checks the middle element of the list. And if that particular middle element happens to be the search key that you're looking for, or the element that you're looking for, then the algorithm will return the matching location. Now, what is a matching location? That's just the index, right? The index into the array, that's what it will return. Now, if the middle element that you are looking at is not the search key, it's not the element you're looking for, then the algorithm will repeat the search on the remaining either left sublist if the search key was less than the middle element, or the right sublist if the search key was greater than the middle element. So what am I talking about here? Well, basically what happens is you start at the middle, and if the middle is not the element you're looking for, since your list is sorted, it's very easy to know whether or not the element you're looking for is greater than the middle element or less than the middle element. And since it's easy to know that, you only need to search one subsection of the remaining array, and this is the efficiency that binary search provides. And we'll look at that in more detail in a second here with a more explicit example. When searching a sublist, binary search begins in the middle of that sublist and repeats itself until the item is found or there is no more sublist. So basically, you start at the middle, it's not the item you're looking for, you check one of the sublists, and you start in the middle of that sublist. Is it the item you're looking for? No, it's not. Okay, you pick one of the sublists made from that original sublist, right, and so on and so forth. So binary search is incredibly efficient in finding an element within a sorted list. During each iteration or step of the algorithm, the binary search algorithm reduces the search space, i.e. the remaining elements to search within, by half. And the search terminates when the element is found or the search space is empty. In other words, the element is not found. You've halved all of the sublists enough to the point where there is no longer a sublist to be halved. And so we'll go ahead and look at an example here. Zybooks actually has good example on the binary search. So we'll go ahead and present this. We can see here, right, the numbers here. This is an array of numbers. You can see the indices right here, 0, 1, 2, 3, 4, 5, 6, 7. And inside of these blocks or cells are the actual numbers that we're looking at. So 2, 5, 6, 14, 16, 24, 32, 63. Notice that they are sorted, so in ascending order. You'll notice that there's a low here and a high here. These are references to the ends of the array in this case. So this is the lower index end of the array and the higher index end of the array. These are actually just variables. You can imagine them as integers representing the indices of this particular array. And how are they going to be used? Well, we'll look at that in a second, but they're actually used to calculate the middle element within an array and any of its subarrays or sublists that get formed from this binary search. You can see here that the search key that we're looking for, or the element we're looking for, is the integer 16. And as we go through the steps of binary search, the white boxes will represent the unsearched items in this array. The grayed out boxes will represent the searched items in this array. And the blue box will represent the current element that we're comparing to the search key, in this case 16. And so the comment here talks about what low and high are doing. The elements within the indices between low and high remain to be searched. So basically what they're saying is they're using this low and high indices to help abstractly represent, or I guess more physically represent, the abstraction of halving the array each time. And we'll look at that in a second here. So we'll go ahead and run this. You'll notice here's their algorithm for finding the middle index or middle element. So basically what they say is, okay, the value of high, which is 7, and the value of low, which is 0, we add them together and we divide it by 2, and they get 3. And so in this case, the algorithm has chosen 3, what is at index 3, to be the middle element, which is in this case has a value of 14. And so yeah, the search starts by checking the middle element. Is 14 equivalent to 16? The answer is no. And so what happens is we're going to check, is 16 greater than or less than 14? And from that result, we're going to pick 1/2 of the array to search through, and ignore the other half. And so there we go, right? If the search key is greater than the element that we're looking for, then only elements in the right sublist need to be searched. And so indeed, 16 is greater than 14. Therefore, we only need to search the right half of the array. And so in order to keep track of what elements still need to be searched, they adjust this low pointer here, or this low reference, to now be equivalent to whatever mid previously was +1. The reason why we have the +1 is we don't need to, once again, research or possibly research that middle element. We've already searched it. There's no reason to search it again. And so basically now low starts at 4, and all the elements between and including low and high are still left to be searched. So we continue running. We adjust to mid using the same algorithm that we did before, so high plus low divided by 2. Well, high was equal to 7, plus low's new value, which is 4. and divided that by 2, and since they're integers, it's rounded off to 5. And so 5, once again being an index, right, has a value of 24. And so now what we're going to do, right, you notice that 14 is grayed out. That's because it's already been searched. And now what we're going to do is we're once again going to check is the current middle, which is in this case 24, is it equal to 16? Which obviously it's not. And since, I'm going to stop it kind of midway here. Let's see if I can stop it at a better point. Let's go back to 3. No, we do want 4. Okay. Here we go. Okay, so what they do here, right, is they kind of jump ahead, but they now do a check to see that 16 is actually less than 24. And so if we look, what this means is we're actually going to adjust high this time, since we know that the remaining subarray or sublist that we're going to check is to the left of the current middle element. And so we're going to move high just like we moved low from before. In this case, the equation to move high to a new index is whatever the current middle index value is, or indice is, minus 1. In this case, it'll be 4. And so what you notice is that actually low and high are on top of each other, which is fine. What this means is you've basically reached the end of the search algorithm. It either must be this element or the algorithm ends saying you have not found the element, or it doesn't exist in the array. And so, if we read the comment here, each iteration reduces search space by half. Search continues until the key is found or the search space is empty. In other words, there's no longer anything to search. And so if we keep playing it, you notice they adjust the mid to 4 and the index 4, and indeed the value is 16, and they compare 16 does indeed equal 16. So we can see here the code for binary search. You can see that mid, low, and high are all integers. And basically, a lot of it is manipulating the values of mid, low, and high as you continue the search through the array. And so in this case, what they do, instead of an explicit check for the array at the middle index, if it's equal to the element we're looking for, they check to first see if what is at the middle index is less than the key. If it's not less than the key, then they check if it's greater than the key. And if it's not less than the key or greater than the key that we're looking for, then we know it must be the key. Therefore, that's what we return. And so they do this while in a while loop, and the while loop's ending condition is while high is greater than or equal to low. So basically, you can imagine eventually low and high will meet, and when they do, you know you've reached the end of your search. And right here is a comparison between linear search and binary search, and how more efficient and faster binary search is on this sorted list. You'll notice here, binary search started at the middle element, which is in this case 11, and they're searching for the element 32. Whereas linear search started at the very end of this list here and is going to try and go through all the elements until it eventually finds 32. So binary search ended very quickly. It decided, the key was not at this middle index here, cut off half of the array, search the other half, start at middle index, the new middle index here with a value of 45, and that is not 32. We know 32 is less than 45. Therefore, check this last element here, and indeed it is 32. Whereas linear search still has a ways to go. The number of comparisons required for binary search was only 3. Whereas in this case, if we continue, linear search requires 6 comparisons. And so this just shows you the efficiency difference between linear search and binary search. So if we go back to the slides, if we look at the runtime, under similar circumstances as linear search, if each comparison takes 1 microsecond, a binary search algorithm's runtime is at most 20 microseconds to search a list with 1 million elements, and 21 microseconds to search a list of 2 million elements, and 22 microseconds to search 4 million elements, and so on. And so if we use the same Amazon example, but in this case for the binary search, searching Amazon's online store, which has more than 200 million items, requires less than 28 microseconds, which is up to 7 million times faster than linear search. Remember, linear search took 3 minutes, whereas binary search, as long as, and this is assuming, of course, that the items in Amazon's online store are sorted, only took 28 microseconds. And so that's all I have for you for this lecture.